Now we'll move to the final topic, the early history of the universe and its implications for the large-scale structures we see. We're just going to look at one point in the early universe, the earliest point in time we can directly observe. We've already seen that the universe is expanding. This tells us that earlier in its history, everything was closer together than it is now. In other words, it was denser and the average temperature was hotter. Before the formation of stars and galaxies, the universe was filled with a mostly uniform gas. At first, this gas was similar to the interior of a star, hot and opaque. Light couldn't travel through it. Instead, light was absorbed almost immediately after it was emitted by the hot gas. That gas was almost entirely hydrogen and helium, with only a tiny amount of lithium, the next heaviest element, mixed in with it. At these high temperatures, the hydrogen was ionized. Remember, this means that the electrons were stripped off of the atoms. So the gas was really a soup of free electrons and protons. However, when the universe was only 380,000 years old, it dropped below 3,000 Kelvin, cool enough that the electrons could combine with the protons to produce neutral hydrogen atoms. We call this event recombination, and it's the first time the universe became transparent.
As we said earlier, before recombination, the gas that filled the universe was like the interior of a star, hot and glowing. But it wasn't until all of those electrons were trapped inside hydrogen atoms that the light the gas was emitting could travel anywhere. Once recombination happened, photons could travel freely through space. The light emitted at this time reflected the temperature of the gas, around 3,000 Kelvin. As we saw back in the chapter on light and matter, a thermal radiator at this temperature produces mostly infrared with some visible light, and a peak in the near infrared. However, in the nearly 14 billion years since that time, this light has been redshifted by a factor of 1,000. So now it's centered in the part of the radio spectrum known as microwaves. We can see this microwave light all around us in space. In fact, if you see static on a television that's not using cable, a few percent of the random signal in that static is actually this cosmic microwave background radiation.
When we observe the cosmic microwave background, there are several things that become obvious to us. First, it's very uniform. In every direction, the first impression we get is that it looks exactly the same. However, as we look more closely, we notice that it appears slightly warmer in one direction than the opposite. This is what we would expect if our own galaxy was moving through space at a speed of about 600 kilometers per second. In other words, our galaxy has its own motion relative to the microwave background. When we subtract this off, there is a faint pattern of hotter and cooler spots, reflecting different densities and temperatures of the gas that originally emitted the light. These small fluctuations in density translate into supercluster-sized clumps of gas scattered throughout the universe. These are the clumps that became the starting points for galaxy formation.
Here's where we can finally tie the evolution of the universe as a whole to the distribution of galaxies, what we call the large-scale structure. As the universe expanded, the gravity of the dense regions we see in the microwave background makes them contract, in much the same way that dense regions in molecular clouds contract to form stars. The much larger clumps in the early universe would have contracted to form clusters and superclusters of galaxies. This series of images shows a simulation of this process over a period of almost 14 billion years. When we map out the large-scale structure in the modern universe, we see that superclusters of galaxies are strung out on long filaments with large voids between them. This looks almost like a collection of soap bubbles in space. In this map of a pair of slices of the universe, each dot is a galaxy, with the Milky Way at the point where the wedges come together. The wedges represent surveys of the universe from our viewpoint. So one of the current challenges in cosmology is working on how the density fluctuations we see in the microwave background lead to the modern large-scale structure. Since most of the mass is in the form of dark matter, these models help us test our understanding of how dark matter behaves, helping limit what the dark matter can be.
To summarize what we've learned about history and structure, our universe began expanding around 13.8 billion years ago. This is the event we refer to as the Big Bang. The matter in the universe started out hot and dense. As the universe expanded, the gas cooled until it became transparent, leaving behind the light we see today as the cosmic microwave background. Denser clumps in the gas contracted to produce superclusters of galaxies in long chains with large voids around them. The mass is mostly dark matter, probably in the form of weakly interacting massive particles, or WIMPs. Finally, the expansion is not only continuing, but accelerating today, leaving open important questions about what the fate of the universe ultimately will be. Now you should fill in this table by describing the causes, as best we understand them, of these cosmological phenomena.
We've reached the end of this stellar astronomy course. This is a good time to look back at some of the big underlying themes of the class. The first theme has been the connection between the sciences. You signed up for an astronomy course, but what you've seen is that astronomy is tied up with physics, chemistry, and even atmospheric science, and they all have to fit together into a coherent whole. After all, labels like physics and chemistry are things humans invented. There's nothing in nature that says this is where physics ends and chemistry begins. So if we want to understand real processes in the universe, we have to use all of the available tools.
The next theme is process. Science is not just about knowing a bunch of gee-whiz facts. Throughout this course, we've seen that what scientists are really interested in is how things work. Not just how hot a star is, but why it stays that hot and what causes it to change over time. It's an understanding of the processes that allows us to make predictions, and it's those predictions that test our understanding of the universe. One thing an understanding of process gives us is an appreciation of how interconnected the universe is. The planet we live on is made of atoms produced in the cores of stars and in supernova explosions. They were distributed throughout the interstellar medium and incorporated into the molecular cloud that collapsed to form our sun and the planets around it. Eventually, our sun will expand out to form a giant star, then die as a white dwarf, producing a planetary nebula that sends more heavy elements out into the rest of the galaxy.
The final theme here is the one that brings most people into this class: general education. Most people who take this course are not planning to become astronomy majors or even science majors. Instead, they're here to fill a general education requirement for their degree or transfer. If you're one of those students, you may be wondering why it is that you have to take a science course when your major is business or history or music or some other field. In fact, the reason for this is very old. It goes back 1,000 years, and it says that when you get a degree, you haven't just learned about a particular field of study. Instead, getting a degree means you've become an educated member of the society, someone who's been exposed to many different fields of learning and many different ways of viewing the world.
So in this course, if you've developed a better understanding of how scientists view the world, what sorts of problems they find interesting, and how they go about trying to solve them, and even better, if you can use this way of thinking in the rest of your life, then you've achieved one of the major goals of this course. That concludes Stellar Astronomy Best of luck on the final exam.